Hello everyone. Uh, another problem. This is a very interesting problem because it will involve some calculus. Okay, so we have a tank. This has some amount of fluid, and we stick a tube and kind of a little bit suck on it, and so the fluid starts to flow. So at this time, set t equal to 0, then eventually the fluid will go all the way to very close to the bottom. We just say all the fluid, a little bit of fluid will be left. We just ignore that, and the question is how much time it takes to do that. Well, it's wrong to assume that the rate will be the same all the time. That's one of the mistakes people make. So we are going to set up more generally. Let's see it at some time t, it's at this level, sometime t, and we use a y coordinate system. So we will need this height here for this point of the fluid. So this is maybe y, this height, this y, and over here when it's coming out, that's y equals to minus b. So y, this point, let's call this point p, and this point q. So yq is this, and y of p will be just y, because one which will be a function of time. And you can see the rate at which this thing is going at v at point p is going to be how this height is going down. Of course, this is negative, so dy dt will be negative. So that's the speed. Over here, the speed here will to speed there. V at q will be area at q, which is a. This and that should relate to speed at p, area at p. And so this is a, and this area here is still a0. So this v at q will be dy dt, and it's a at p over a at q, which is just, this is a over a, a0 over a, right? a0 over a, a0 is okay. So this will be in the given symbols. Okay, so one of the equations we will have is the conservation equation, which is this equation, and the second equation we'll have will be the Bernoulli equation, because we're going to assume there's a non-viscous flow, so I'm going to have Bernoulli equation. So how do we set up Bernoulli equation? I'm going to set it over here. Bernoulli will be so at this point, so I'm going to set up at point P and point Q. So there's some pressure here, pressure at point. So there's no fluid over here now. At this point, fluid top is here. Top here at T. So Bernoulli at T, at time T. So there's some pressure here. And pressure, this is atmospheric pressure. Half rho, the V at P square plus rho G, and the height at that point is y at P, which is equal to y, equals to, when I look on this side, the fluid is coming out this way. The pressure that's opposing it is also atmospheric pressure. So this is also atmospheric pressure. This is very important to realize what you're pushing against. So it's not like P0 plus rho GH. So this is, for instance, this is not the atmosphere. So this is against which I'm pushing, right? So this is the most important. A lot of people make a mistake here. So this is atmospheric pressure, because when the water is coming out, what's opposing it? So we have to ask this question. Ask when water is coming out, what pressure is opposing it? That's what you have to ask, and the only thing opposing is atmospheric pressure. So that's the question. Then I have a half rho VQ square plus rho G, and it's minus B. Why for that is minus B? Okay, so these guys will have dy dt square. So now let's see, some simplification took place over here, and I can send this guy on this side and send this guy on this side, and so we have half rho VQ square is going to be this way. So we're going to have a dy dt square, and this will be a0 over a squares, because I have square VQ square, minus 1. That just equal to, on the other side of a rho g y plus b. So all of this is constant. So you can see rho got removed from here, and then put 2 on the other side. So this becomes 2 on this side. This can be put on this other side. So this will be a0 square minus a square minus 1 on this other side, and this 2 will make it, everything is, this is half, this is half, this half. So this is the only thing that's going to be, the dy dt is negative. So when I remove the absolute sign, I'll have to put a minus sign there. So let's see. So I'm going to remove the absolute sign and put a minus sign there. And you can see that this whole thing is constant. So let's call this some C. So we have an equation here. So this equation becomes dy dt equals minus c is square root of y plus b. Now this can be integrated, right? So you can say dy over square root of y plus b equals to minus c dt, and this one just basically 2 times dy square root of y plus b dy equals minus c dt. And so when integrate, how much do I integrate? Y has to be 0, some height y0, which is some height, so y at times 0 is the original height, which is v0 over h0. Y final time we want is 0, or approximately 0. So we get we go from h0, y equal to h0, to y equals to 0, and we go from y equal to t equals 0 to t equals to t. And so this is 2 is square root of b minus square root of y h0 plus b equals to minus t. So t is equal to 2 times square root of h0 plus b. C is down here, minus square root of b over c. C is this whole thing. C is 2g over a naught square minus a square times a square is square root of that. So that's the answer. And you can see that the rate at which it is flowing is actually not constant. So as y is coming down, because y starts from this value as coming down, and it is actually when y is 0, it doesn't hit the bottom at 0 speed. It actually has some speed. Okay, so this is a pretty famous problem. It goes by the name time to empty a tank or drain a tank. You can actually do an experiment. You can take a big container and make measurements of all of these things, and you actually find it's very close to. I've done this experiment, so I know this formula is very close to what time comes up in experiment. Okay, so I just remind you to have more of these problems at www.physicsbootcamp.com, .org, actually not com. And don't forget to subscribe. You can get notifications when I post videos. I will see you in another video. Bye.